In 1808, English chemist John Dalton united Lavoisier's understanding of elements and compounds with Boyle's insistence on the particulate nature of matter. In his book, A New System of Chemical Philosophy, Dalton proposed that all the atoms of a particular element are identical and different from those of other elements. The crucial and measurable difference was the atoms' masses. Hydrogen atoms are the lightest, oxygen heavier, sulfur heavier still, and iron even heavier. This made sense of the fact that compounds are always composed of fixed ratios substances by mass. For example, the iron in a sample of iron sulfide always accounts for 63% of the compound's mass, however large or small the sample. The rise of the scientific approach to chemistry led to the discovery of several new elements in the 18th century, and Lavoisier's definition of elements and his insight into the role of oxygen in combustion helped to speed up the rate of discovery in the 19th century. Many new metals were isolated from their earths, oxides, by removing oxygen. The invention of the electric battery in 1799 gave chemists a new tool for chemical analysis. Electric current can decompose a compound that resists most other forms of analysis. Several new elements were discovered using electrolysis, electrical splitting, in the first 3 decades of the 19th century. In the 1860s, 2 German scientists, Robert Bunsen and Gustav Kirchhoff, added another important technique to the practice of analytical chemistry: spectroscopy. Using an instrument they invented, the spectroscope, Bunsen and Kirchhoff studied the spectrum of light given out when particular elements are vaporized and heated. They studied the emission spectra of all the known elements, and the presence of unfamiliar lines in the spectra of various substances led to the discovery of several previously unknown elements. By this time, chemists began to realize that the growing list of elements seemed to fall into groups according to the properties and reactions. Sodium, potassium, and lithium are all metals that react with water to produce alkaline solutions. Chlorine, bromine, and iodine all react with metals to make compounds like common salt. English chemist John Newlands noticed that elements in the same group seemed to be spaced 8 elements apart in a list of the elements by atomic weight. Newlands' scheme only worked for the first 20 or so elements, and other chemists ridiculed him. However, Russian chemist Dmitry Mendeleev found similar periodicity when he organized the known elements into groups based on their properties and reactions. In 1869, Mendeleev formulated the first periodic table, revealing at last a sense of order in the growing list of elements. One of Mendeleev's master strokes was leaving gaps in his table where elements would fit when and if they were discovered. From their positions in the periodic table, Mendeleev could predict the missing elements' atomic weight and chemical properties. Within a few years, several of the missing elements had been found. The discoveries of the electron, radioactivity, and X-rays in the 1890s were the stimulus for a dramatic era of atomic physics in the first half of the 20th century. The existence of small, light, negatively charged electrons showed for the first time that atoms had inner structure. The behavior of electrons explained how atoms can form ions, how atoms form bonds, and why some elements are more reactive than others. Using radioactivity, in 1911, the New Zealand-born physicist Ernest Rutherford discovered the atomic nucleus, a tiny, dense, positively charged particle at the center of each atom, and proposed that negatively charged electrons orbit the nucleus. Dutch physicist Antonius van den Broek originated the concept of atomic number when he worked out that each element had a different number of positive charges in the nucleus, corresponding to the number of electrons in orbit around it. In 1917, Rutherford discovered that the nucleus was made of particles, which he named protons. In 1913, Danish physicist Niels Bohr used the nascent theory of quantum physics to work out that electrons travel around the nucleus only in certain specific orbits, and found that changes in energy of electrons moving between the various orbits matched the spectra Bunsen and Kirchhoff had studied. The very highest energy transitions emit X-rays, not visible light or ultraviolet, in 1914. English physicist Henry Moseley found a correspondence between the positive charge of an element's nucleus and its X-ray spectrum. This allowed him to refine the periodic table, arranging elements precisely by atomic number, rather than atomic weight, and to predict two more unknown elements. The discovery of the neutron in 1932 completed the basic understanding of atoms, including the explanation of the occurrence of isotopes, different versions of the same element with differing numbers of neutrons in the nucleus. See page 8. The theories and experiments of nuclear physics enabled physicists to work out how elements are created by the fusion of protons and neutrons inside stars and supernovas. Nuclear physics also led to the creation of elements heavier than uranium, most of which do not exist naturally. See pages 153 to 157.